My name is Amy Perfors. Thank you for coming to my talk today, my virtual talk. Today I'll be talking about modeling work I've been doing, modeling trust and the emergence of echo chambers in populations of Bayesian agents. And this is joint work with Keith Ransom. So the motivation for much of my work has been the insight that, for humans at least, a lot of our knowledge comes from other people. So these are things where the truth is out there, so to speak, but it's difficult for all of us to access. So, these are situations where we don't necessarily know about the mechanisms involved. We have to learn from other people, and therefore we have to make inferences about who to trust. So some examples include things like, did Trump assist the Russians to influence the US 2016 election? Now, unless you're Trump or the Russians involved, you probably don't know directly. And so you have to figure out who to trust, figure out what evidence is real, and so forth in order to decide on this. Similarly, if you're trying to figure out if vaccinations are safe, unless you are a doctor or have the right kind of medical or statistical training, you probably can't decide this for yourself. So you have to figure out who to trust, what sources to believe. And the more scientific training you have, the better, but still there's an element of inference involved, social inference. And of course, this happens all the time in social situations when we're gossiping or trying to figure out what's going on. Did Alex embezzle funds? Again, unless you're Alex, you probably don't know, and you have to figure this out. So this is a hard epistemic problem. And the question that I was confronted with is, in this situation, if you're a completely rational learner, what should you do? So being a total nerd, I decided that the way to approach this is to actually try to simulate such populations of rational learners. And let's make it as easy as possible for these learners. So let's assume that everyone is Bayesian, rational in that sense at least, and they all communicate with each other fully. So no one's lying, and you can talk to everyone as much as you want, all right? And you can model situations like this, either sort of as fully connected graphs where everyone's talking, or as sort of chains, and in many cases they end up converging the same thing. And there's actually a lot of previous work looking at the convergence behavior of these chains or systems. And so, for instance, we know that they converge to a shared prior if there's no external ground truth, if they're just talking amongst each other and there's not data coming from the world. So pictorially, you might sort of say, okay, these are their priors. These distributions, they communicate by sampling from the distributions, and the shared or the behavior of the system converges to that prior. If data comes from the world, then the convergence is affected by the structure of the world and the sampling from there. But if the prior isn't shared, that's when you start to get even more interesting things happen. What you see is that those with the stronger priors have a distorting effect on the chain. So if you have something like this, that person in the upper left has a very strong prior to see only sort of dark circles. And that person isn't going to end up distorting the systemic behavior. And so even though everyone else has milder priors, the system as a whole is going to end up looking more like that strong prior. And this kind of result suggests that the process of information transmission itself can distort group belief, even if everyone involved is rational. So the problem is, the learning problem in the real world is even harder than this, right? So it's not just that people might differ in their priors, some might actually be actively deceptive, or they might be completely wrong. And if there's no external ground truth, it's really hard to tell who you should believe. So given these factors, I was interested in asking what happens when rational learners try to share information and learn from each other. So what I'll be reporting on is a series of simulation studies with groups of Bayesian agents. The first ones have smaller numbers of agents, but we vary that. Later on, we sort of can have even, I report on things with many more. But basically the idea is these are fully connected agents. Anyone can talk to anyone else. And each agent is performing a joint inference task. They're trying to figure out which other agents are trustworthy, and they're also trying to figure out which hypothesis best describes the data. So the hypothesis learning is just, they're trying to learn something about the world, but they're also trying to figure out who's trustworthy, who they should believe. And so they're calculating a joint posterior. The hypotheses in this case are just two-dimensional Gaussians, but you could think of this as they're trying to communicate about, say, a two-dimensional category. What is the nature of that category? And they communicate by sampling from their posterior. So no one's lying. No one's doing any weird distortion. They communicate by sort of sampling, hey, this thing I think is a likely piece of data. And what we vary is how heterogeneous their prior beliefs are. Does everyone share the same prior, or are they different? All right. So first, I'm going to report on some initial results, a baseline where it's as I described, and then a ground truth where it's the baseline situation, except instead of only talking to each other and all data coming from each other, there's a little tiny bit of external data that comes from the world. And I want to see what that does to change the system behavior. So in the first place, where all data comes from other agents, everyone talks by sampling data from their posterior. What we can do, and what I'm particularly interested in doing, is measuring the degree of trust and polarization in the system after it converges. And we can measure that by something called the Gini-MD, which essentially puts a numerical quantity on the amount of polarization, say, in a system. So for instance, these two blocks, the one on the left represents with 6 agents, the one on the right is with 18. It sort of shows all their pairwise mutual trust. So dark means there's a lot of trust. So in this is a Gini-MD of 0.1. There's a lot of mutual trust. Everyone's talking to everyone else. On the other hand, you have, say, a Gini of 0.5. And in these populations, it's split into 2 echo chambers, more or less. So the people in one block are only talking and only trust in each other, and people in the other block only in each other. And so that's a high Gini. And of course, sort of the other Ginis kind of interpolate. And generally, you can see that basically a Gini of somewhere between 0.3 and 0.4 indicates a very polarized population. And so the question I'm interested in is, what kind of populations do you get? All right. So let's look at this. And what I vary is the number of agents, that's in the panels, and the heterogeneity of the priors. So homogeneous, everyone starts off with the same priors. Heterogeneous, they start off with pretty different priors. And the Gini-MD is on the y-axis. Higher means there's less trust. And what you can see is that basically as it gets more heterogeneous, there's much more polarization. And in the heterogeneous, fully heterogeneous condition, you can see that in the majority of the runs, it ends up completely polarizing. And you see the exact same thing with 18 agents as well. So basically, the more heterogeneous populations were very likely to polarize into echo chambers. And this is, again, with fully rational agents. And when you think about it, it makes sense, right? If you have no idea, if there's no external source of ground truth, you have to figure out who to trust, then after a while, you start listening to only some people because others you think are less and less likely to be trusted. Everyone's doing the same thing, and you end up polarizing. Now, what happens if we add just a little bit of ground truth? Give everyone some access to something that they all agree is reality. And you can think of this as something like, say, climate change. Everyone for a long time argued about, is it happening? Now we're all seeing the world getting hot. That's a bit of ground truth that that everyone has access to. So what happens if everyone has access to something? Okay, so all I do is add the exact same thing, but sort of vary the proportion of the data that they receive that is the ground truth. Here I'm just looking at the heterogeneous condition because that was where we saw the polarization in the first place. And the first things I've graphed are when the proportion of ground truth is 0. This is basically a replication of the previous thing. As you can see, there's a high polarization. Most people end up not trusting each other. If we add ground truth, then you can see it's actually quite nice. By the time you're only even 4% of the data is ground truth, you're down to the majority of the simulations end up not being polarized. And by the time it's 6%, nearly all of them. So it doesn't take much ground truth to dramatically lower polarization, but you have to have some. So that's good news, somewhat. It's a mixture of good and bad, I suppose. So far, we've shown that basically, if they're just talking to each other, there's no ground truth, you get polarization is very, very likely in populations with heterogeneous beliefs. But even just a little bit of ground truth will make a difference. So the open questions after this is, well, it's fine to say, everyone has ground truth, but in the real world, that's not the case. Some people have more access to others, say through expertise or just, they're there. What happens if this is unevenly distributed? And then the second thing you might ask is, what happens if, instead of agents trying to learn who's trustworthy and also learn about the thing, what if they're not, also trying to learn who's trustworthy? That is, how many of these dynamics are driven by people or agents trying to figure out who's trustworthy? And maybe we could stop this polarization if we stop that. So that's my last two questions here. Addressing the first, what I did is vary two things. What proportion of the total available is the ground truth? So that's what we did last time. But in addition, vary what proportion of the population has access to that ground truth. So you could imagine that, if 2% of the data is ground truth, but only 50% of the population has that might be really different than if 2% of the data is ground truth and all of the population has access to it. So this is kind of a complicated graph, but each of the panels is showing how much ground truth there is available, and the y-axis showing the proportion of the population with no access to that. So here, when there's 0% ground truth, then basically everything is the same. This is a replication of the very first study. And you can see there's a lot of polarization. You can also see here where I've varied the percentage of ground truth, and everyone has access to it. So this again is replication of what we've seen. We see the ground truth has a big impact. So the question is, what happens in the rest of these panels? And you can see on one extreme, so when there's 10% ground truth, then basically the more and more of the population that doesn't have access to it, the worse polarization gets. So for instance, if only on the rightmost thing, if 83% of the population doesn't have access to the ground truth, even though there's 10% of it, it doesn't really stop polarization. And you see a similar pattern throughout. And if you do a regression on this, basically both of these things are highly significant, the amount of ground truth and the access to it, and they have similar coefficients. So they play very similarly sized roles. So really both matter. And then the second question is, well, do we get all these effects just because the agents are trying to learn about trust? What happens if instead of trying to figure out who to trust, they just tried to figure out what content to trust, what specific information to believe? So here we have sort of changed it so the agent is only performing inference about the hypothesis. They're also not learning about trust. But the way they perform inference about the hypothesis is the same as before. The hypotheses that seem more likely, given their priors, are going to be believed a little bit more. Another change we made is basically to check the robustness of these previous results. We made it a one-dimensional Gaussian instead, which allowed us to sort of be able to simulate many, many more agents. This is just to make sure that those modeling assumptions weren't driving our results. So what I'm going to show you here is just sort of a typical trial. Here we have the iteration of the trial, and belief is basically for each agent what they believe on this one-dimensional Gaussian. And so what you can see in this typical trial, this shows a bunch of agents. They all start sort of heterogeneous all over the place in beliefs. They talk to each other, and what we see is the emergence of 4 different echo chambers in this run. And this is fairly typical. When agents can, discount the data that they disagree with, even if they're not performing inference about trust, then you still get polarization. And if you want to sort of see this in action, these things are weirdly compelling. You can see it sort of start to happen. Again, this is sort of a very representative type run. And if you vary the heterogeneity and the size of population, basically as before, the more heterogeneity, the more distinct echo chambers you get. But it happens very, very commonly unless everyone pretty much already starts at the same point. Now there's one interesting side point, I think, which is that you find that agents change their mind generally because of people like them, because you discount people who say something that's completely unlikely given your current beliefs. Then the way to get people to change their mind is to have people who are similar to them but slightly different say something. That's going to be more likely to change minds. I think this is a side point given what we know of the humans, and also because in terms of what it means for one of sort of my future directions. So the implications, I mean, these are all simulations here, but I think it has interesting implications for psychology and the world we live in. The first is, I think that simulating these systemic effects of individual differences in cognition can actually be revealing about the information dynamics. And especially sort of looking at it in terms of, you know, what a kind of rational learner in a hard epistemic world does, I think can sort of, illuminate why we might have this pervasive problem of echo chambers. In this sense, polarization in echo chambers is not irrational. You know, it's a kind of standard, a thing that you might expect if you have populations with heterogeneous beliefs with very little access to an external truth or agreed upon external truth. Improving that access does do a very nice job at lowering it, but you have to sort of have that somehow. The things I want to look next is basically, this was all set up actually to some of my real questions, which is how aspects of our current information environment contribute to polarization. So one of the things I want to do is simulate the presence of bots. Before, we've had all sort of, just nice agents speaking to each other. But if you actually wanted to drive this, these simulations suggest that it's probably much more effective to be the bottom bot than the top one. Start where people are and then pull them away. I think this is how bots actually work, but this, if we're currently simulating this, and this might sort of explain why. And the other thing I'm really wanting to do is simulate the effect of frequency distortion. Essentially, sharing and retweets are a way of non-sampling veridically from people's hypotheses, and that itself, I expect, will lead to more polarization all by itself. But we'll see. So for now, I'll end and say thank you very much.